to make in this field in our understanding of ultracold molecules, right? So how they behave, how their levels work, how they interact with each other, what they do when we shine some laser light on them, like all kinds of interactions. The molecules are really a new frontier. Okay, so even matter antimatter asymmetry problem, you would be probably surprised, but
Even with recording level.
yeah, I think I'm fine. Here's my phone. I'm trying to. Oh, it's here. Sorry. So anyway, so the ultracold molecules are extremely important, and so this is just to give you an idea. Kirby molecule is one of these molecules that has been created for the first time in 2006 in the group of Juni, and now over, I think, dozens of labs, around a dozen labs in the world, they have alkali dimer molecules. And this is what the energy level structure of the alkali dimer molecule looks like. So Kirby has 30C, it has ground rotational state and the first rotational excited state. This is just vibrational electronically ground state. This is just rotational hyperfine structure. 36 levels and n equal to 0 manifold, 3 times more levels and n equal to 1 manifold, and then hundreds more levels if you try rotationally excited. So this is this amazing complexity that really drives a lot of this research, ultracold molecules, right? So, and our research in my group and in many other groups have been kind of touching like on these issues and how to really use those extraordinary complexity, right? We don't understand much here. We have been kind of like starting to make sense of the energy level structure and this limit. And we actually have a paper on the archive now where we're proud. I'm going to mention it quickly later in this talk. I think we have understanding here, but so far all the experiments have been mostly operating in a large magnetic field limit where nuclear spin degrees of freedom are actually decoupled from rotation. So this structure arises from coupling of rotational motion of molecules with their nuclear spin. So just that, there's not even vibration. So you see this multiple weight crossings, lots of interesting stuff. What's more, these levels, some of these levels, mostly unequal, and if you take two levels here, n equal to 0 and let's say n equal to 1, they're going to be coupled by traditional electric dipole moment. And therefore, these levels will experience long range and isotropic and tunable electric dipole-dipole interaction. So this electric dipole-dipole interaction is really the key to using to a lot of applications in ultracold polar molecules. So this, for example, as even a single molecule is actually pretty good quantum, perhaps computer, right? So we can even claim, right? Because like you can store information here in this n equal to 0 manifold, which has long coherence times, actually about seconds. Now I think people went to a few seconds, and they can even go to many. So you store here, then you excite it to these levels, and you do quantum information there, your quantum gates, then you de-excite it back. So molecules have everything. So even a single molecule has infinitely many potential energy, right? So, okay. So basically, a lot of the things that are unique to molecules are, of course, rotational states, right? And like I just mentioned, like this seminal paper by David and Miller was the first to use these rotational states to engineer dipole-dipole interactions. So this kind of engineering can take different forms, but the first observation, as far as I know, was done by Juni's group in the Beijing group in 2013, where they observed coherent hopping of rotational excitations caused by the long-range dipole interactions. And this research is going very strong. So last year, for example, itinerant spin dynamics was observed. This is a very significant observation because itinerant spin dynamics can hold the key to extremely long-range interactions and therefore generation of highly entangled states that are very relevant for things like voltammetrology and measuring something beyond, with a precision that extends beyond the standard quantum limit. So this is very nice. Quantum gates have been observed. I don't have here two papers that came out in Science earlier this year by John Doyle's group and Lawrence Jones group at Princeton. So they observed this kind of interactions causing coherent like sloping gate. So this kind of interaction, what it does, it one molecule n equal to 0, it excites a neighboring molecule into n equal to 1 rotation state and de-excite the original molecule from 1 to 0. So excitation actually is made to hop from one side to another, and this is of course sloping quantum gate, but also origin of all these interesting interactions. In my group, in particular, trying to understand this quantum dynamics of ultracold molecules using some realistic models, and not just limited to exchange interactions, but for example, recent observation of Rashbach resonance by Wolfgang Ketterer's group was very surprising in collisions of two diatomic molecules, because no one ever expected this narrow, long-lived states in molecules. And Wolfgang's group just found one. It is 25 milligauss wide, and it was a shocking and extraordinary discovery by experimental group, because it shows that states that long-lived states that can be used to do quantum information do exist in collisions of molecules. Like this is a 4 atomic molecule with hundreds of channels, like rotational, which is hyperfine, chemical reactions can happen. Nevertheless, there's this super narrow Rashbach resonance, right? So anyway, so we developed some model for it, but it's still largely, I would say 99% of this remains outside what we can do currently, because it's a super extraordinary complexity of this scattering problem, which has billions. My estimation, this one has about 1 billion scattering channels or something like that. But the most we can solve currently is about 10,000. Okay, so we're a long way away from understanding what the nature of this long-lived state, right? Which would be really interesting, right? So, but unless we develop and quickly develop some very powerful algorithms for reducing the computational complexity of this problem, we are pretty much down, like not in the dumps, but in the dark about this, remarkable phenomenon. And the field is limited, right? The progress in the field will be limited unless we understand better collision processes. And of course, this is not a good place to start because of this super complexity. Other molecule collisions can be better, but that's a topic for another talk, right? So,
but where is this state, long-lived state? You said collisions. I'm thinking about things colliding.
Yes, it's a resonance. So it lives in the continuum. It has it's a coherent superposition of a bound state and a continuum state that has a very long lifetime.
Can I say it's a bound state dressed by the continuum?
Yes, it's like a Rashbach resonance.
Well, I don't know what that is.
Oh, Rashbach resonance is just when you have a closed channel, a bound state, coupled with dressed with open channel state, and as a result, the wave function has a peak at short, like where typically bound state has a peak. So it has this bound state quality. So it's kind of like a bound state.
And it also is long-lived.
Yes, it is. Yeah, well, it was technically observed in inelastic scattering experiments, but that would be too, going too far. But pretty much, yeah, it's long-lived. You cannot explain it, and we've done a model on this one. You have to make an assumption that there's a long-lived state. Otherwise, you just see flat continuum, right? So that is but the origin of this is completely mysterious. Yeah, and this is something that stimulates me every day to work and get up, in the morning. We work on this horrible problem. So, yeah.
Can I ask what was surprising? Because I thought like collisional resonances are sort of ubiquitous in these collisions.
Yes, very strong inelastic losses were expected, and when you have a very strong loss, resonance cannot occur because of the universal character of reaction dynamics. So-called sticky collisions happen, and everything is lost, and it is a very magnetic field, and people search for this in other molecules they haven't seen. So this was the first, and that was only one. So they scaled magnetic field from like around 10 Gauss to about 1500 Gauss with a step of, you can see this, a fraction of a Gauss. So it's a remarkable experiment. They only saw one anyway. So that was still, like it shows they all, some bright problems, but it also poses perhaps more questions than answers. Okay, so
did they search over a certain rate? They have some expectation for, I guess, the density of states for the system, right?
Yeah.
So did they find fewer states than they expect based on the density of state estimate?
Right. Yeah, we haven't really done much in the way of density of state estimate because this is open channel molecules. It's highly complicated. So far, they have done density of states. It's not my cup of tea. So I didn't do exact calculation. Density of states calculation is done by other groups, and I think I'm sure they're working on this. Gotcha. So maybe answers soon will be able. Yeah. So. Okay, so but I mean, what I'm really going to talk about today is this, right? So it's amazing molecule. Fullerene molecule is an example of a polyatomic molecule, and I've already shown you the energy level diagram for diatomic molecule, right? Can you imagine what happens when you have 60 atoms? Like it's going to be just a mess, pretty much, right? So and you would be right. if you, right, if you think about this, but fortunately, this has a high symmetry. And this is what makes it possible to actually do quantum calculations of energy levels on this molecule, because it's amazing icosahedral symmetry of the molecule. Actually, the dynamics is, or the energy levels are quite accessible to calculation. So one can actually go and explore wonderful quantum phenomena in this molecule, such as quantum ergodicity, which is something I'm going to tell you about today. But before I go, I'm just going to flash this result. We also have been working on generating many-body eigenstates molecules with Julius and Anna-Maria Ray's group. And we have more new results from 2023. You can actually generate long-lived nuclear split states using certain quantum entanglement protocols, which these nuclear split states, they live for a long time. I already told you about that. And you can use them once you prepare this long-lived nuclear, let's say, cluster state. You can actually do measurements on it and do, measurement-based quantum information protocols, stabilizer operators and all of that. So this could be quite useful, although of course this hasn't been demonstrated yet experimentally. We're looking forward to new experiments there. So anyway, so what I'm going to tell you about today is a general topic of research that's called quantum information dynamics. So quantum information dynamics is really important, right? So especially has been studied extensively in many quantum many-body systems, where in quantum quenches experiments, right, when you create a non-equilibrium state population in some sort of quantum many-body system, spin shading or something else, and then you just watch it, you time evolve it, and you see how these interactions cause the system to thermalize, and questions like thermalization, of course, the famous eigenstate thermalization hypothesis that was suggested some years ago, and black hole connections and entanglement, they all play a role with quantum information propagation. So pretty much in many quantum many-body systems, this is a question of big, of huge interest. And the experimenters are using quantum gas microscopes, Tweezer arrays to address these questions. But kind of like the question we have thought about, like why not use molecules, right? Molecules are amazing quantum few body to medium body systems, right? And maybe many body, like DNA or something. So why not use molecules? Why haven't anyone thought about using that? That's an amazing question. Quantum information propagation. And now different groups are starting to explore this question. It's by no means my own group. My collaborators, other groups are looking into, for example, there's been a recent paper on quantum scrambling in clinical reactions. So amazing work by Rubler group at the University of Illinois. But other groups are also kind of interested. But the key question here is basically how does quantum information propagate in interacting quantum many-body system? So the questions about thermalization, ergodicity, are important, and quantum information scrambling, because this is really a particularly important question, because a big, how do you access information? How do you measure a quantum many-body system, right? So you typically use local probes. And if that happens quickly, your information quickly becomes inaccessible to your local probes, like I don't know, in the center somewhere, and trying to measure information. So no, sorry, you cannot do it because the information is gone, not coming back to you. So what you learn about this quantum many-body system using local probes is limited, essentially, right? So this is an important question, of course, related to questions in condensed matter physics, which I'm not expert in, so but I just mentioned it here, just for completeness. But largely speaking, loosely speaking, previous work has been limited to quantum many-body systems. Molecules have much to offer with them. So, what is really quantum ergodicity? So this is the question that we will be investigating today. So, ergodicity essentially means that a classical system explores the entire phase space around it. So basically, if you start your system like a billiard or something like that, right? So it's a spherical one. So the trajectory of a particle that's moving inside is not going to explore the entire phase space, right? Not the entire space in this case, in coordinates. So it's just going to bounce back and forth, but eventually it's integral, right? But on the other hand, if you have an ergodic system, eventually some sort of stadium billiard or something like classic examples from classical physics, right? You have this trajectory just bouncing back and forth and eventually filling the entire space, right? That's what ergodic means, right? Essentially in classical physics. What it means in quantum physics is kind of shakier proposition, right? Like what does it really mean ergodic in quantum physics? Different people you ask, may give you different answers to that, right? Like, but no, like some people think, for example, non-ergodicity is actually essentially lack of thermalization. So, right, so ergodicity means like if you have certain conservation law, of course, the trajectory is not going to leave that space. Let's say that's defined by energy conservation. But in a quantum system means, okay, it's going to explore the entire space available to it in some ways, right? What does it mean for quantum system to even do that? That's a good question. Lack of thermalization, integrability is one answer to that question. Another answer is that eigenstate of quantum systems tend to be localized, let's say in some space, in some, whatever space you prefer. But it actually, it depends on the kind of subspace that you're analyzing your system with respect to. So that's not unique definition. So as far as I know, there's no unique definition of quantum ergodicity or non-ergodicity.
So the phase space also, it's in the reciprocal in the momentum space as well?
Yes, exactly. But of course, you have to take into account conservation rules. For example, if energy conservation should be on the energy shell, so it shouldn't leave, right? But so quantum ergodicity typically people characterized by highly delocalized eigenstates, or they look at energy level statistics. So there's this paper by David Leitner, who is in the chemistry department of UNR, so we talked a lot. And really, quantum ergodicity has a lot of chemical applications as well. Because like if a system is ergodic, and quantum ergodic, that means oftentimes, and the connections there haven't been, as far as I know, fully understood. But also, you can use simple theories, such as, for example, Rice-Ramsberger-Castle-Marcus theory, which is RRKM in chemistry. And so you can apply this kind of simple phase space arguments to say, okay, the system fills the entire phase space. Then, we can just replace our averages, I don't know, with something like thermal averages, and we can just write down the answer. We can calculate a lot of things, like reaction rates, most importantly, using RRKM, if we know that our dynamics is kind of ergodic. But is it ergodic? Most of the time, the answer is actually no. People have studied this question, and don't get me wrong, I'm not, not claiming to. This is, for example, a recommended review, but it has like hundreds and hundreds of references going back to 50s, like 60s, where people, even beginning with, John Marcus, Marcus, like himself, he just postulated this ergodicity, but then it was later found that many systems do not exhibit quantum ergodicity. So for many systems, you should not expect simple theories to work, which is something kind of, in chemistry, right? If you look at the deviations of RRKM rates from normal rates, can be like all over the place, 5 orders of magnitude, 3 orders of magnitude. So the theory can be just complete rubbish, really. So for systems, and the underlying reason for that is that it's not ergodic. Many systems do not explore it. They do not like to explore the whole space. The eigenstates are highly localized. And in molecules, so this question in molecules can shed light not only on just general physics questions like symbolization, quantum information scrambling, but also on chemistry questions.
So when you say localization, do you mean like in Hilbert space?
It depends on the space that you're referring to when you analyze. So you can introduce a basis in Hilbert space, right?
Sure.
And then analyze localization with respect to that basis. It means that, roughly speaking, how many states in the basis cover one single eigenstate from another basis. Let's say you have Hamiltonian, you have an eigenstate, right? That's uniquely defined, but you can expand it in different basis sets. So let's say in typical basis, I don't know, like product basis, like for let's say single particle basis, right? What's how many of those basis functions would enter the expansion of the eigenstate? This is a typical measure for quantum ergodicity. It's called inverse population ratio, IPR.
So, but could you find it where you have in one basis it's highly delocalized, but in another
Absolutely.
basis is
Absolutely. That's why I said it's not well defined.
Yeah.
So it's not. But so the basis typically you want to analyze. I mean, there's limited choice for a large system. There's a limited choice of this, basis sets. But typically, like people just expand in product type basis, which is what we do, for example, for molecules. But I'll show you later examples. But if you can come up with some fancy basis set, sure. So ergodicity is definitely basis set dependent. That is the definition. Yeah. So basically, like the group of Jun-Yi at GILA, they had this amazing experiment where they were able to actually cool the C60 molecules down to very low temperatures and measure its rotational spectrum. So that was a feat because it wasn't possible until 2019, but by cooling methods and using ingenious cooling methods and spectroscopic techniques such as frequency comb spectroscopy, they were able to actually dissolve these individual rotation conditions, and these little numbers, they're actually total angular momentum states. So they actually go from about 40 all the way to about 310. So the rotational constant of C60 is pretty small. I think it's a fraction of a wave number. So even at cold, let's say, argon temperatures of the buffer gas, the pretty large population of very high excited rotational states. So that allowed you to do spectroscopy as a function of rotational state and also look at the spectral lines. So and what they observed is actually quite interesting is, well, at low values of total angular momentum J, you see that there's no, I mean, it's pretty much, so these vertical lines are just expected positions from rigid rotor, like spherical top calculations. But at high values of J, you see that they observed these little additional splittings, right? And so each line was split. And turns out actually in C60 molecule, the rotation of the molecule interacts with vibrational modes. And because of that, there are these additional terms in the Hamiltonian that are lower symmetry than just the full spherical top, which is like SO3 cross SO3, right? And so it splits because of broken symmetry. So it turns out there's a broken symmetry that causes this echosahedral splitting that were observed for the first time in this amazing experiment. So what was, I mean, to analyze the energy level statistics to get some insight into quantum ergodicity, other theorists in calculated some energy levels, and the group of Nomial at Harvard, they did this analysis of rotational consecutive level spacing ratios. So this is similar to the normal level spacing you would see from, when people analyze chaoticity versus non-chaoticity. Like, remember, chaotic spectrum of eigenvalues indicates it means energy level repulsion, right? So if you have energy level repulsion, it means that you have quantum chaos. That has been kind of the paradigm here. But they actually used a better technique by, I think, Bogolny in one of those recent, papers that he suggested, analyzing not just the level spacing ratio, but actually the consecutive level spacing ratio. So they take the next one divided by the previous one, and the previous one divided by the next one. So, and then the minimum. And so it turns out if you can do this analysis, you get a better handle on quantum chaos than if you just compare it to just standard level repulsion. But these are just theoretical details. They're all in this paper. But the point is that what was seen was actually quite surprising, because like as a function of J for low values of total angular momentum, you see the statistics is quite ergodic. So it's indicative of ergodicity, normal, ergodic as expected. But then suddenly at J equal to 120 to 140, you see a completely different level spacing statistics. So that actually indicates a transition to non-ergodic behavior at higher values of J. You see transition back to ergodic, right? So that is actually very interesting. And that yes.
So I'm used to seeing, roughly 3 possible values for this, right? There's 0, there's 0.39, and there's 0.53, and
Yeah.
whatever the GUE is.
Yeah.
So what does it mean that these are scattered all over the place? Like, I've never seen a log plot.
Well, it's calculated. We have to analyze at a given value of J, right? Because it's a constant of the motion. So it's closely conserved. And when you vary that, what happens is that your energy level patterns change, because Hamiltonian actually effectively Hamiltonian does depend on J. And then you analyze it at a fixed J, because you are not, you're looking for signature of level repulsion. So you're not. So that's why I think that's the origin of this, because like there's this tensor interactions that cause transition like in energy patterns as you change J. And so that actually causes this scatter, I think.
But the usual story is that even with like sparse interactions, you look like a GOE matrix.
Yes.
Right. So you should be 0.53, not 0.4, whatever.
Right.
So is this like how many are they averaging over eigenstates in the window? How many?
I think
is
so.
that?
I think so, but they're not averaging. I don't think they're averaging over capital J.
Right.
So
That's a tunable.
Otherwise, no level of repulsion. Right?
Yeah.
Because it's a constant of motion.
Yeah.
But yeah, I think it's a good question. I think it's not something that I've done. So Professor Yang's group will be better qualified to answer that. But yeah, that's kind of the point is like, yes.
Can I ask a follow-up question? So in one of your previous slides, you mentioned the non-ergodic distribution of eigenstates follow a specific distribution. I forgot what it's called. That's
Yes,
what,
this one probably, right?
yeah, the Wigner-Dyson statistics.
That would be ergodic, yeah.
So
Random matrix.
how does the experimental results compare to?
So definitely ergodic, yeah, ergodic would be the answer for those lower, the lower and higher bands.
It looks rather flat, whereas this looks more peaked.
Yeah, so this is level repulsion, right, in the case of ergodic behavior. And some people count. Random matrix ensemble describes this Wigner-Dyson distribution. So there's no very small probability for having levels at spacing at very small value. So they like to repel each other. Whereas here, Poisson means that there's a high probability of kind of bunching of them being together and not experiencing much of it.
But I guess is there quantitative agreement between this Wigner-Dyson statistics and what
Yeah.
experimentally
I
observed?
think so, yeah, they were able to fit, but it wasn't like exactly that. It was like Bogomolny's statistics. It wasn't this.
It was sort of a hybrid of.
Yes, exactly. It wasn't advanced because Bogomolny wrote a PRL like in 2010 saying that I can do better than Wigner-Dyson and it kind of worked. So he was better able to discern features, like tell one distribution from another based on the ratios as opposed to just level spacing distributions. But I'm not right. So this is Norman's magic. So that that I'm sure they know very well better than me. Yeah.
The other, I guess, both the question and comment is, so like when we talk about ergodicity, it's a dynamical attribute, right? It describes the dynamics in system.
Well, not necessarily. You can think about it in terms of eigenstates.
I see, okay.
And
I guess that's sort of my comment is there is no dynamics done here. It's
no.
looking at ergodicity purely from the sort of level repulsion.
Yes,
Eigenstates
exactly. Well, this is
perspective.
pretty common. I mean, you can look at ergodicity like in a classical ensemble, you would probably look at trajectories filling the entire space. But in quantum, I mean, there's so many approaches, right? So, and they're not really square sometimes with each other because you can look at eigenstates, you can look at distribution functions like, Husimi distribution function. You can look at like people are still working on the best way to kind of discern. Yeah. Oh, no question.
Kind of like question. So like if I think of those spectral speed, like they have both resonance and also liveness. So does the spread or the broadening of those spectral features have any like implication, or does that affect what's to be expected for those?
Yeah, for sure. The broadening, I think it was this experimental, they did take into account, of course, broadening but I wouldn't, I'm not sure what exactly the kind of the source, the mechanism for broadening. Yeah, but it's a low vibrational spectrum. So basically the transition is from the ground through vibrational manifold to one of those extended vibrational modes. So it's not electronic, it's same electronic state. Okay, so basically this allows us to make a conclusion that basically this is actually a transition that was observed from ergodic to non-ergodic and back as a function of total rotational movement is actually the first transition that was observed as a function of rotation. So people in the field observed quite, well, actually this paper I should of course begin with, right? So this is Victor's paper that tells you that these features, that high symmetry features can be promising for encoding qubit and for doing quantum error correction for large molecules. And this lack of ergodicity actually means good news for large quantum systems such as C60 molecules. It means that the information doesn't fully spread out, doesn't fully thermalize. You can actually have you can use it as a potential for quantum memory or something for storing quantum information. And generally, lack of thermalization is always good news for quantum information prospects of a system. So, but I also want to mention that typically people observe this transition, and I should have made a historical note, of course, before that there's vast literature where I observe this ergodicity similar transitions as a function of vibrational number deposited in the 70s and all the way up to the 90s. People were exciting molecules and from ground electronic state to excited vibration state using varying amount of energy. And then what they saw is the so-called IVR threshold, where you put a little bit more energy, suddenly the system becomes ergodic. But below that energy, it's completely non-ergodic. So this is so-called IVR threshold phenomenon, and it has been demonstrated with many large molecules, including organic molecules. But so this is the first demonstration of similar effect as a function of rotation. So it hasn't been done as a function, but it wasn't even known that it can actually occur as a function of rotation, but it does occur.
Can you explain more about why is it, which one is it, ergodic or non-ergodic at low energies and then higher energies it becomes the other one? Why is it?
That's not known. So we see the transitions, but we have a hypothesis that's maybe due to some dark states that actually cross with this.
So you didn't even care about any Hamiltonian or anything, you just took the experiment, analyzed the statistics, and then showed they follow these different distributions that can be classified as ergodic and not.
Right, well, we calculated the energy level. So the energy level calculation was important for the assignment of spectral lines. So like, for example, here.
Fit it into different J's.
Yes, and this degeneracy is like, you see this little 10, 11, this is the number of, because it's a fully symmetric, it's a rep of the icosahedral group. So that's how many a rep.
That's
The
right.
energy levels are in this total angular momentum. So that was actually one of, well, that was something that I was responsible
Why does the group theory calculation? You already know that in the tables. but-
for the sixth order, yes. But if you go to higher order tensor interactions, it's been unknown. And so what my job was, in fact, that I actually was able to calculate the energy levels for the tenth order icosahedral tensor. And that was, and the way I did it, I took the group tables for the A representation in the sixth order, and I diagonalized the Hamiltonian and used those as a basis functions. So in this way, I was able to actually calculate the energy levels to all orders using the good symmetry basis function. That was the only way to get the good symmetry wave functions. Well, there are other ways. You can actually directly calculate asymmetry icosahedral spherical harmonics, but
Yeah.
that's a horrible prospect if you want to try that. There's only one paper, and they only look at a rep, and there's like numerical density. So there's like coefficients that go like huge numbers. And as far as I know, like some crystal people did that, like,
Yeah.
but it's, you know, very hard to do. So there's a simpler way to do it using this Harkin-Patterson tables, which you go to sixth order, and then you diagonalize, you extract the wave functions of asymmetry and then use them as a basis. And that way you generate an asymmetry basis. So now I can give an asymmetry basis. For
So the base is the hard part, the number of 80 reps inside a given J.
No, that isn't
That's
hard.
Yeah.
There are wheels. There are these wheels that you can calculate the
Yeah.
in Hartran papers, but triangle influence can be kind of hard. So
Very different question. When you say high energy, do you mean like near the middle of the spectrum, or so infinite temperature, or do you mean near the top of the spectrum? So,
oh, you mean like in the IVR is a norm in the historical node?
so when you're talking about these, the C60 transition from non-ergodic to ergodic back to
Yeah.
non-ergodic,
Mhm.
it's like is the high energy non-ergodic stuff at infinite temperature or at negative?
No,
up near the top.
No, it's not a thermal. So it's still a spectroscopic experiment. So there's like a distribution of
Yeah.
thermal distribution at a lower, like let's say J equal to from let's say it's 40 to 300 in the ground vibrational manifold, and then there's also the same distribution in the first excited vibrational manifold. So and then transitions are made between all these thermally populated levels in the ground manifold all the way up to the thermally populated ones, according to selection rules, of course, in the vibrationally excited manifold. You know, there's no R branch, P branch, and Q branch. Just like this.
So let me rephrase my question. I'll take energy so that the trace of the Hamiltonian is 0, right? So the ground state has very negative energy, right? This is, I don't know, random field Heisenberg. So when you say high energy, do you mean energy near 0, or do you mean energy positive? Or do you mean, or is this all at very negative energy close to the ground state?
So those levels, right, that are being calculated. The spectral line shape depends on the wave function, both the initial state and final state, because it's an overlap. So I think the answer to your question is like in a way both. Very low energy and very high energy, but not the middle. Because like it's a spectrum, right? So the transition intensity is the Frank-Condon overlap between on the bra function is rotational. Let's say you're starting from initial vibration state, the final vibration state, and then in the middle there's transition dipole that couples them, right? Times some radiation. So in all of that is involved in the spectrum. So I'm not sure I can answer your question.
Yeah, I think we're
Maybe you can ask me.
later, perhaps.
I'm not sure if this is well posed when you talk about those historical contexts where people also observe this transition. Like, so should I think of this as like a quantum phenomena, or is it also just anything that has like a whatever structure that can be related to some kind of random matrix, like I would expect it.
Right, quantum phenomena.
Or
I
like
think it has to do, like, this IVR transition has been studied to death by many groups in the 70s and 90s. And I think some of them try to relate it to this phenomenon of many-body localization, where you can actually, like, vibrational modes would be like your sites, and then you have this harmonic couplings. So this is Martin Gubel, David Leitner's work at the University of Illinois. So yeah, I mean, there are connections to quantum many-body physics there. But those are due to vibrational modes. So yes, I think the answer to the question is like, yeah, there are connections. Yeah.
Is there also the rotational structure that's a T1 mode, yes, the same as the ground state?
Rotational structure is different because V1 mode has different. So that would be going into details of like this nitty-gritty details of spectroscopy, but pretty much the tensor character. It's not 612 tensor, but I think it's like more like 713 because there's like vibrational angular momentum in the vibrational excited state of 1. So you shift it. But turns out we did calculations also including this what's it called? Coupling of angular momentum. So it's like 6 and 10, but it's like 7 and 11 or something like that, 7 and 11. Right. So that thing is not affecting the spectrum too much. So we can actually assume that there's no vibrational momentum doesn't really play that much. Yeah. So anyway, so this actually this is very strange. So we're really looking for interesting models, and I've been thinking about some models of explaining this effect, but that's hard because I think it's just due to some dark vibrational states that are intruding the spectrum and causing these changes in tensor parameters and transitions from ergodic to non-ergodic behavior. But I just want to make a comment. So we also thought about, after we made this, like, can we, perhaps control quantum ergodicity? So P60 is sensitive to the total angular momentum, but can we use external fields? And actually, the idea goes back to Eric Heller's paper on ergodicity of Porcer versus Parr and aminobenzonitrile as a function of electric field. So here's a very nice paper showing that actually this degree of ergodicity on these two isomers of the same molecule changes as a function of electric field. But that was just theoretical result. Beautiful one. So how can, that's an alternative measure of quantum ergodicity, where he basically looks at so-called inverse population ratios. He basically, so this is the coefficient of expansion of given eigenstate, let's say A, in terms of like some other basis state, A. So N is the eigenstate and A is, some other basis state. So basically calculate the squared overlap, which is like the fourth degree of actually the square participation ratio, which is the fourth degree of overlap between the two basis functions. And then you invert it. So this physical meaning is like how many states from basis A participate in the eigenstate AN. So basically when you expand N in A, how many functions you have. So this is a measure, it's called inverse population ratio. And he basically plotted this all. One means like, it's just one. So there's not much of a spread. So which means like dark means not so ergodic. But when there's a lot, it means that one eigenstate spreads over pretty much the entire A basis set. So it means that there's like very ergodic. So I really like the paper.
Oh, is it just because like your Hamiltonian has higher terms that kick in only at high energy and they'll mix things more up? They'll mix things up more?
It depends yes, I think you can say that, but it has connections with time dynamics for sure. So you can actually evolve the physical meaning of that. You basically start some state, which is not an eigenstate, you evolve it under the system Hamiltonian, and you look at how many states eventually.
It's the same thing. Hamiltonian determines time evolution.
Exactly.
The more mixed up it is, the less symmetry it has, the more it'll kick you around all over the corners of the Hilbert space.
Yes, exactly. So that means that these states are very localized in some corners of Hilbert space, and these red states are very delocalized. And the nice thing I saw in this paper was really nice. You can control it with electric field. So I thought, okay, let's take a look at some molecule we can do, right? I cannot do benzonitrile, but I begin this talk with KRB molecule, and I know this switching happens. So my student Rebecca, in collaboration with Anna Maria at GLab, so we decided to look at KRB, right? Because KRB is a great molecule. We have a code that produces energy levels. So, and that was actually quite striking, because if you change magnetic field from 0 to 400 Gauss, you see this ergodicity of the levels in the ground rotational state manifold. Remember, those are hyperfine states. So they're like nuclear spins interacting with rotation. Here, not much changes. But if you look at rotational excited states, you see this tremendous change in ergodicity. Actually, as you change magnetic field, and this is, sorry for this overlapping zeros, but this is like 400, this is not 4,000 Gauss. Okay, so 400 is very reasonable. You can do it in the lab. So people, before they work in this limit, they start to avoid this crazy ergodicity or spaghetti. I showed you some spaghettis. So they don't like this, but we actually try. So this makes us kind of to begin to understand, right? So what's going on here? So as you lower the magnetic field, you see the ergodicity, it becomes very ergodic, and the maximum kind of ergodicity is avoided crossings of the states, which is kind of understandable because like this is where avoided crossing is where the two states kind of approach each other and spread, right? Into like, so you get like 1/2, roughly speaking. But you actually get even more because it's not just determined by one basis state, but we checked like 6 or 10 basis states. So it's like highly ergodic. But the good thing is that because you can change nuclear spin state in the magnetic field, you can control them. You can actually, so here the nuclear Zeeman interaction wins over. So basically, it's like in rubidium atoms. I don't know how familiar you are with rubidium atoms, but you have this Paschen-Bach effect, right? When you have a large magnetic field, the nuclear spin and electron spin decouple. So the magnetic field, so basically the magnetic field takes so the nuclear spin wants to orbit precise around electron spin, right? But when the magnetic field is strong, the magnetic field tears apart this like nuclear spin and electrons, but just wants to process independently, right? And so that means that the eigenstates are just orbit states. So they were very highly non-ergodic, right? So just one single product state. This is what we see here, actually, except that now the role of nuclear spin in rubidium is played by rotation in Tscherbul, but it's roughly speaking the same Paschen-Bach effect when you go to high magnetic field limit. But at low fields, the magnetic field can no longer hold on to these nuclear spins and then start to couple to rotation. When they couple to rotation, that's where the beautiful stuff happens, because rotation depends on, rotation gives you electric properties on the moment, right? Like electric dipole moment. When you look at this, for example, this is striking. It means the electric dipole moment of KRB can be changed from 0, that's all magnetic field, all the way up to this, constant value that you find in textbooks. So that's because people neglected the nuclear spin, but actually the nuclear spin plays a huge role. You can actually make KRB molecule non-polar. So if you're a chemist, this should we should use Rotten Tomatoes now on me, because like I'm changing the electric properties of molecules in my magnetic field. And I can go from 0 to maximum value. This, of course, is theory, right? Okay, so no one has verified this, but it's crazy, right? And this really all happened because of quantum ergodicity of energy levels of coupling between the rotational states and nuclear spins. You cannot really decouple at low magnetic fields. Anyway, so I think this is really cool because you can control electric dipole interactions between molecules just with magnetic fields. And this gives you an additional norm to understand. Should also work for other molecules in principle, like higher, like laser cooled molecules, calcium, strontium fluoride, any alkali dimers, like we just tried KRB, but it should also work for sodium lithium or other dimers. So we really think that this ergodicity has some bright future. And just one thing I want to flash here is another project we have been working on. Is another crazy idea. Ultracold molecules with my former postdoc and Lincoln Carr from Colorado School of Mines. So the idea here was actually use ultracold molecule-based quantum simulation to simulate open quantum systems. And the idea here is basically use rotation as a system, and then you use nuclear spins in the molecule as a bath. So you may recognize this as a celebrated central spin model in actually here at the University of Maryland. Of course, quantum dots are studied for quantum computations, and this is like an extension. But imagine a quantum dot made of rotations, not an electron spin. There's no electron, but there's like a rotating molecule. But actually, all the parameters of rotation are very similar to electron spin. Like frequencies are in the gigahertz range, so you need to apply some magnetic field, of course. Here, you don't have to worry about magnetic field, right? So it's even better. Perhaps you can realize it. So we call it the central rotor model. It's like the extension of central spin model to where you have a rotating molecule being responsible for the system. It's like a system, and the bath is just the nuclear spins, but the nuclear spins just sit on the molecule, right? They come with a molecule prepackaged, right? So you get your molecule and then you get the nuclear spins, right? So anyway, so that was kind of the idea, and you basically you start with this product set. The way you call this quantum system, you start in a rotational state, you create a rotational wave packet, and you wait under this Hamiltonian, end up with molecular rotation being transferred. The quantum information that was originally in rotating molecule over time is going to get into the bath, right? As usual in the central bath model. So it goes into nuclear spins, and then you kick the molecule, you kick it with a laser pulse, and a Coulomb explodes. And if you think this is science fiction, think again, because this has been demonstrated. It's actually imaging of molecules by a Coulomb explosion is a great way to image rotational motion. You basically like strip the electrons away from molecule and it explodes, right? This is how you actually work with rotational packets. So this is a way to detect, the nuclear spin path via rotational motion, right? So because they talk to each other. And so anyway, so we're just working on a paper. So hopefully it will be of some use to someone. Okay, so I think I'm out of time almost, so I don't have time to talk about this entanglement, but it can be done. Cluster states can be created. Spin squeeze states can be created. Conclusions. Okay, so this is conclusions from another part of the talk, but so anyway, C60 is great. It's quantum ergodic and quantum non-ergodic, depending on J. And we can use ultracold polar molecules, especially spin degrees of freedom, for a lot of interesting things. So thank you for your attention.
Lots of questions during the talk.